Let's start. Dear partners, hello everyone. I'm Steve from Cost Power's Overseas After Sales Department. Today, over about 50 minutes, we will run a systematic customer training session focused on the commissioning and the subsequent day-to-day operation and maintenance of the Poland SLAM 01 1MW 2MWH energy storage project. The following table about atom and details. Our project is SLAM 01, and our audience for the whole owner, representatives, OM team, EPC team, and EMS integrator. Operating strategy. Shaving is not enabled for this project, as confirmed by the customer. You provide the EMS using a single communication network. About the electrical interface, the main transformer converts 15 kV to 690V for the PCS. The auxiliary transformer output 400V. The operating mode, grid connected only, not islanded load supply. The whole delivery time about 50 minutes. Today's agenda has 6 parts. The first 2 chapters build a shared understanding of the project boundary and the product architecture. Chapter 3 and 4 focus on the commissioning release conditions and the item you need to confirm and cooperate on during commissioning. Chapter 5 covers daily operation and maintenance after commercial operation. And finally, we leave 10 minutes for on-site question and answer. So, everyone, follow my pace and draw down any questions as they come up. The first, chapter 1, user environment. First, let us start with the overall boundary. Please picture a main power path in your mind. Your 15 kV system connects to the HV side of the main transformer, which steps 15 kV down to 690V, and our PCS is connected on the 690V side. In addition, there is a 400V auxiliary transformer dedicated to powering the auxiliary systems. Look at this map. Please look at this system interface diagram. Refer to the top view layout script. We are looking at a top view layout of a battery energy storage container. This is a standard 20 feet ESS container. External dimensions 6058 mm for the length and 2438 mm for the wide and 2896 mm for the height, commonly called the 6058 high cube model in the industry. The container is functionally divided into 3 zones. First, the cooling and the control zone on the left, the battery cluster array in the middle, and the PCS power conversion zone on the right. First, let's introduce the battery cluster array. In the middle is the core of the whole container. We can also call it the heart of the container. 5 battery clusters labeled the battery cluster 1 through cluster 5, from bottom to top, from here to here. Each cluster is marked at both ends with the main negative and the main positive terminals, which are the key nodes of the DC busbar collection. The 5 clusters in parallel from the container's battery stack, corresponding to a single container capacity of about 5 MWH. During SAT, what we focus on verifying is the torque of each cluster's positive or negative connections, insulation resistance, and the inter-cluster voltage consistency. So Next part is here. Cooling and control zone on the left side. From to the bottom. At the top, as the SDA aerosol 100G or E condensed aerosol fair separation unit. The water spray interface. Here, the water spray interface. The external fair water source connection point. The liquid cooling unit circulating an insulin glycol water solution through the cold plates at the bottom of the battery clusters. Keep cell operating temperature in the optimal 15 to 35 degree range. The exhaust outlet for repaired pressure relief after fire agent release, and at the bottom, the control cabinet, housing the BMS master controller, communication manager, and the protection relay. The next side is the PCS and the DC side. On the right side of the container is the PCS cabinet 1, the power conversion system cabinet, responsible for converting DC to AC and feeding it to the grid. Between the PCS and the battery clusters sits the DC distribution or DC to DC module, which handles DC side protection, measurement, and disconnection. Next part is safety and fire protection. We also called it three-tier defense. The safety design of the container is the highlight. It deploys 3 tiers of fire protection. So, first tier, 1 SDA aerosol 100G condensed aerosol at the top and 1 at the bottom, plus 3 bottom aerosol A for repaired separation at the early stage of the seal terminal runaway. Second tier, in container, smoke temperature and gas detection linked to BMS powered reduction and PCS grid disconnection. Here, smoke and temperature. The third tier, the water mist interface on the left. Here, external water source connection as the final fallback for cooling. This configuration complies with the UL 95408 and the NFPA 855 fair test baselines, and is a mandatory SAT check item in Europe and in the US. Next part, ventilation and smart monitoring. On the container roof are for air intake, fan controller, and the inlet port camera. On the right is an air inlet make-up opening, forming a complete intake or exhaust airflow organization. At the bottom is the temperature and humidity sensor, reporting in real time to the EMS for linked cooling and ventilation. When smoke or abnormal temperature is detected inside, the BMS immediately reduce power and trigger fire protection. The last part, closing design philosophy. To summarize, this layout follows the design principle of battery in the center, electrical equipment on both sides, control nearby, fire protection full coverage. The whole container has a protection rating IP55, operating temperature from less 30 degree to 55 degree, and supports both sea and land transport. In subsequent SAT, we will verify each component's installation, position, and wiring one by one according to this layout. So that's all about the layout. The chapter 2 is about product introduction. It's about product itself. This unit is a 20 feet liquid-cooled AC or DC integrated container with a rated energy of 2.089 MWh using 314 AAFP. It's short for life host PO4 cells. The system consists of 5 battery clusters, each 417.996 kWh. Each cluster contains 8 battery packs plus 1 high voltage box. Each pack is built from 52 cells of 3.2 V in a 1P52S configuration, giving a system topology of 1P416S-5. So the 5 cluster DC circuits converge to the PCS, and the manual specifies a PCS power of 1075 kW. On the AC side, the 15 kV or 690V main transformer steps 15 kV down to 690V to feed the PCS, while the auxiliary transformer separately supplies 100V. Regarding the controlling, please understand it by the responsibility boundary. Your EMS is outside our scope. The project uses single network communication and does not deploy peak shaving control logic. Please coordinate with your EMS integrator and advance to confirm point table read, status monitoring, basic control authority, time synchronization, and communication interruption and recovery strategy. The following table about the subsystem, product menu information, what you should monitor. It's about battery system, main transformer PCS, and auxiliaries, terminal management, fire protection, communications, and please notice this. Don't worry about this document. I will give our customer after my training. It's an important map. Well, please look at this communication and protection architecture diagram. First, opening system overview. We are looking at the communication and protection architecture diagram of an energy storage system. This diagram shows a completely ESS containers 4-layer communication architecture from EMS dispatch down to cell acquisition and the 3 major protection chains. The core basis for communication testing and joint commissioning during SAT. Layer 1, EMS dispatch layer for the EMS. At the very top is the EMS, we also call it energy management system, the brain of the whole storage plant. The EMS connects down via LAN Ethernet to an Ethernet switch, which in turn links to the PCS, power conversion system, and the BAU, battery alarm unit with screen. The LAN port carries the 4 remote functions. Modbus TCP protocol runs on this path. Layer 2, power and alarm layer. On the left of the switch is the PCS, the power actuator, receiving EMS charge or discharge commands and power limit commands. On the right is the BAU with the screen, the alarm and the display unit inside the battery container, connecting via 485 or CAN to signals of all battery clusters, liquid cooling, fire protection, access control, and other subsystems. The BAU is a in-container signal aggregation point and also the human-machine interface of the BMS inside the container. Layer 3, battery cluster layer with BCU. Here, going down is the BCU, battery cluster unit, the battery cluster control unit. The diagram shows BCU1 and BCU5. Actually, they have corresponding to the 5 clusters in the container. Each BCU connects upward to BMS CAN bus and manages one battery cluster downward. The BCU I or O include what? First, about DC circuit. Cluster level DC side protection and current HV2, HV or LV box contactor control. High or low voltage switching within the cluster via a HV or LV box. 3. Fuse. Cluster level short circuit protection. 4. Cluster current management. For total voltage acquisition or cluster insulation, cluster total voltage acquisition and cluster insulation. Okay, that's layer BMU and cell. At the bottom of each cluster are 8 battery packs, battery 1 to battery 8, like BCU1. Okay, each with a BMU battery management unit. The BMU connects upward to the BCU via CAN and acquires each cell voltage and temperature downward. This is the bottom layer of data and the source of SOC or SOH calculation. 8 packs cluster minus 5 clusters, 40 racks, 40 packs. The full cells data acquisition point of last parts about safety and fair signal network. The blue signal flow on the right side is the in-container safety and fair protection link, stringing together all dry contacts and in 3 groups. First, for equipment status group unit, liquid cooling feedback. This is liquid cooling feedback, emergency stop, container cabinet size, distribution switch status, container size, UPS fault, fail level 1, level 2 alarm, failure alarm, combustible gas, and fan fault, combustible gas, low concentration alarm, aerosol feedback, and so on. Look at the picture, you can find it. Next part is the light and the PCS group for field lamp, PCS no or NC dry contacts, distribution switch excitations. Next part is environment monitoring group for PCS and liquid cooling unit, fire protection, liquid level, temperature, humidity, fire lamp, dehumidifier, altimeter. So all the signals are reported up to the BAU, to all the signals reported to who? To BAU through the I/O moving equipment interface. The BAU performs logic judgment and reports to the EMS via line. Yes, via line. And upon any anomaly, the BMS responds in 3 stages: power reduction, grid disconnection, and fire agent release. So that's all the map. It's the reference 3-level BMS architecture. Your EMS and the PCS use the system level status and permissible power consolidate and validated by the BMS. Okay, next, Chapter 3. Pre-commissioning prerequisites. Chapter 3 covers the pre-commissioning conditions. In first subsection, the cable schedule is the main line for commissioning release. Reviewing the cable schedule, do not look only at the model and the length. So please confirm these 12 items per circuit. Unique tag number, function, voltage, class, start point, end point, number of cores or parallel runs, pulse, squeeze, or polarity, capillary, terminal aperture, bolt, tightening, toe, shielding and grounding, routing path, and responsible party. If any single atom does not match, commission cannot be released. So, the full cable schedule spans 3 pages in the manual. Please check it page by page. The following table is about the release package and the required evidence and for the design baseline approved single line 15 kV or 690V main transformer and PCS circuit, 400V auxiliary transformer optional ATS 400V backup circuit, AS built and nameplates for your team or EPC team. Electrical conditions, main transformer impedance, vector net earthing and protection coordination approved, 15 kV, 690V and 400V auxiliary supplied ready. For your, please see it and read it. For the most important at this table about the safety and organization. So please make sure the switching permits, work permits, LOTO, LTO, emergency stops, fire protection, installation, boundaries, PPE, two-person operation. Must make sure two-person operation for safe. Dispatch window and emergency contacts are ready. It's very, very important. Double P, must double. That's what I told before. In subsection 3.2 about this map, project-based confirmation of the full schedule. 2 key reminders, please. First, at the PCS AC termination, the pulse screens of the 690V main circuit, parallel cable current sharing, lock aperture, bolt grid and torque must match the final product interface and the final schedule. Second, fire and waterproof sealing at the cable entrance must be done after the cumulation test, and the as-built photos must be clearly show the circuit labels, soldering scope, and the construction date. Please notice this and read it carefully. That's the whole project confirmation of the complete schedule. First, circuit for main transformer from a 15 kV AC power cable. Please your team or EPC team confirm the model, terminations, length, and test under the approved 15 kV design. 2. PCS to main transformer 690V main power circuit. Use the final schedule to confirm that parallel runs, terminations, and to match the manufactured PCS and the main transformer's 690V set. 3. Protective earthing circuit. Confirm size, quantity, terminations, route, and boarding under the final earthing calculation. 4. Box transformer ATS 400V backup circuit optional. Whether to include is your decision. If included, confirm source, capacity, ATS, logic, protection, cable, and responsibility boundary. 5. For control cabinet 400V auxiliary supply, BSS3 pulse screens, natural earth arrangement, terminations, and protection. 6. Video, cascading fiber or line. Confirm medium interface lines, shielding, patch, panels, and system boundary. 8. BSS2 transformer communication line. Verify ports, V line or IP, shared earthing and labels. Reference PCS AC termination area, pulse screens, current sharing of parallel 690V cables. Lug hole size, bolt grade, and Tokyo must match the finished interface and final schedule. Please notice, apply fire and water sealing after cable tests are complete. As built photographs should clearly show circuit levels. It must be clearly. Sealing scope and installation date. EMS protection and document freeze. 3 additional loops must be closed before commissioning. First, the protection loop about settings, operating screens, and reset authority for the PCS, 15 kV or 890V main transformer, 400V auxiliary transformer. Second, the communication loop. Your EMS read status and measurements correctly through the single network. Basic control and execution feedback stay within the approved scope. Chapter 4, cooperation during commissioning, and we need you to confirm during commissioning. Chapter 4 covers the items you need to cooperate on during commissioning. During commissioning, your side holds the station level control authority, the work permit authority, and the acceptance conclusion auxiliary. The customer must designate at least one person with electrical work experience and on-site coordinator. If multiple people are involved, the responsible person must appoint one as the chief coordinator. The table shows the stage, and every stage you need to do something. First, for the document and the site briefing, confirm the single valid revision, identify power sources, installations, emergency stops, fire systems, earth points, network cabinets, and hazard. 2. Static inspection. Check every circuit against the compliance schedule. Endpoints 690V may circuit pulse screen. 400V auxiliary circuits, PE Tokyo labels, sealing and test report. 4 staged energization. You should notice for one switching operations for high voltage switch gear shall be performed by your power team. Our commissioning engineer do not oversee the qualifications for the switching operations on high voltage switchgear, include ring main units and corresponding high voltage electrician certificate. So the chapter 4 covers the item you need to cooperate on during commissioning. That's I have already told before. Say it again. First, during commissioning, your site holds the station level control authority. The work permit authority and the acceptance conclusion authority. The customer must designate at least one person with electrical work experience as an on-site coordinator. If multiple people are involved, the responsible person must appoint as the chief coordinator. Energization must be confirmed step by step. After each step, first verify voltage, pulse, squeeze, status word, alarms, insulation, contactor or breaker position, and the emergency stop chain. Only proceed to the next step once everything is confirmed correct. If the actual state ever disagrees with the step table, stop, preserve the screen and record, confirm the insulation boundary, and then let the responsible party troubleshoot. Here I want to stress strongly on the commissioning step. It is absolutely forbidden to bypass interlocks, mask protection, or arbitrarily change settings to rush the schedule. Also, before remotely controlling the PCS, please confirm local remote mode, control authority, grid connection status, power limits, and unacknowledged alarms. 5. Daily operation and maintenance. This chapter covers daily operation and maintenance after commissioning. Please assign at least 2 people to each operation. One executes and the other supervises and verifies. Peak shaving is not used for this project. Manage the equipment under the approved standby, operating and stop modes, while continuously modulating the 15 kV or 690V main transformer, PCS 400V auxiliary supply, BMS single network communications, alarms, and environmental conditions. Please assign cabinet opening, leave measurement, terminal removal, or protection or seating change to qualified and authorized personnel under a work permit. This table shows each stage and every stage we should do and operating design decisions. Let's look at the first. Before operation, verify your approved operating mode, EMS basic control authority, SOC, BMS permissions, PCS availability, 15 kV or 690V main transformer, 690V main circuit, 400V auxiliary supply, terminal management, fire protection, single network communications, and open alarms. Make sure or confirm that all actions remain within approved limits. During operation, we should notice record charge or discharge the energy, planned charge or discharge completion, ending SOC, max or mean temperature, voltage division, alarms or events, and operators confirm approved standby. If a division occurs, identify the limiting source before deciding to continue, derate, or stop. After operation, record charged or discharged energy, peak window complete, ending SOC, max, mean, temperature, voltage division, alarms, events, and operators. Confirm approved by status. And create work. It means if you found, please use screenshot and event and daily inspection use trend, not a normal signal reading does not prove a normal trend. Please compare historical data under comparable operating conditions. whether battery temperature spread is increasing at the same power. When rack current remains low, PCS thermal rise week by week. Liquid cooling supply return temperature difference or pressure changes. All single network packet lose clusters at a particular time. Trend drift over appears before operates. Give your team time to arrange a planned outage and qualify. The table shows area, daily check, and your action. Just read it. That's the reference of a PCS cabinet. Reference to the protective earthing. So what you should do after an alarm. Preserve evidence first. Record time, operating mode, EMS target, PCS actual power, SOC, permissible power, status words, alarm codes, event screens, and related trends. 2. Assess the impact. Distinguish adversary, power limitation, protective stop, fire risk, or personnel risk. Identify whether the source is BMS, PCS, EMS, communications, thermal management, or plant system. 3. Act within authority. Operators perform only reset, mode changes, and stop defined in the approved SOP. Escalate cabinet installation, termination, protection setting, or software work to specialist. 4. Confirm recovery conditions. Resume the approved standby or operating state only after the course. Corrective action. Result and approval are recorded. Repeated alarms must not be hidden by repeated reset. For the chapter 6, for question and answer, we have some questions for this chapter. But after this you have any other question you can ask us. First, is peak shaving enabled for this project? No. You provide the EMS using a signal communication network, but no peaking shaving control logic is configured. Commissioning and acceptance cover only approved status monitoring, measurements, protecting interlocks, basic controls, communication loss, and they do not include peak shaving schedules for benefit very. 2. What's the PCS AC side? For this project is the 15690V main transformer, 15 kV to 690V, and the PCS connects to the main transformer's 690V side. The PCS AC main circuit is therefore 690V, and the 690V value in the cable schedule. Question 3. Where does the project 400V stop? The auxiliary transformer takes supply from the 690V side and converts it to 400V for auxiliary systems. Please keep the 690V main power circuit separate from the 400V auxiliary circuits. Their cable, termination, switchgear, and protection data must not be mixed. The 400V supply powers low voltage auxiliary loads, including on-site cooling fans, cabinet heaters, lighting, and control powering. Question 4. Is the box transformer ATS 400 secured mandatory? Please read it. Don't worry, I say it again. The documents will give it to you after. So, this questions, that's all. Thanks for here. See you.